History of Astronomy, Part 1. Test results 2017. We had a really strong group of people last year, averaged 85%. This year, the average was still good. It was 80, almost 81%, not as good as last year. There were a few of you down there in the 60s and 70s, which should not have been. I pretty much spoon fed that first unit to you, so study, buckle down, study, okay? Welcome to the new school year. Get to it. So, astronomy used to be to help with planting and harvesting crops. So you see the moon, full moon. Farmers used to plant and harvest the crops by the full moon, new moon. Also by the constellations. They notice certain constellations come up every time, the same time each year. Much more accurate than the old maps. Our maps didn't get, or maps, our calendars did not get very accurate until Caesar Augustus, and then they started getting more accurate. So their large structures were built to help measure more precisely when certain dates occurred, based upon when the sun was at a certain point in its ecliptic, or the moon, or the stars were all lined up in a certain way, based upon our Earth's orbit around the sun. So Stonehenge is one of those. It's huge, still kind of a mystery how that was put together. Huge, heavy rocks before we had big machinery. So Stonehenge, the Bighorn Medicine Wheel, this one right here, they all served as some sort of an almanac. Practical values, obviously, ships' captains would navigate. You're on the ocean, you have nothing but the stars and the water. The moon, it helped a bit, but the stars were huge. You see under the word direction, under the D, would be the North Star. This is called a circumpolar picture. They aimed the camera on a tripod straight at the North Pole. They then opened the shutter lens and left it open for probably an hour or two. And the stars then made trails as our Earth rotated on its axis. If you took the angle of the star trail, took 360 degrees orbit divided by the angle, you could find out exactly how long they left the camera open. So the Caracal Temple was another astronomical masterpiece back in the day. The ancient Chinese did something long before the telescope was invented. That's why the word's ancient, like 2,000 years ago. Chinese actually, with their naked eye, stared at the sun. I know we used to do this as kids, but we weren't good enough to see sunspots. They first observed sunspots with their naked eye. And obviously, it had to be a few of them to collaborate and agree we see so many spots rather than just spots that appear on our eyes from looking at such a bright object. Boom! Sunspots with a good solar filter, very easy to see. In 1054, all across the world there is documented a huge star which just appeared so bright and slowly dimmed after several months. And we call that a supernova, 1054, obviously because it occurred in 1054. Supernova is simply a star which has gone through all its fusion to the point where the core gets so dense it just explodes. And one huge explosion sends off tons of energy and also shoots out dust and gas for millions and millions and millions of miles out from the core. The remnant of that supernova from 1,000 years ago almost is now the Crab Nebula. I guess it kind of looks like a crab. Nebula means it's fuzzy. It looks fuzzy because it's a lot of dust and gas that's still lit up by stars and protostars within it, but it's slowly accreting again to make stars. Of course, it's going to be a long time, millions of years before that occurs. And we'll be gone. The Arab astronomers, they added math and their knowledge of math to astronomy and really helped us determine exact dates for their holidays, their holy days. Cosmology is cosmos, the sky, celestial sphere, what's out there, ology, study of. So study the workings of the universe. The Greeks Said the universe is nothing more than just the sun. We saw that every day. It would come up in the east, set in the west. The moon, it did the same, but it slowly moved around us. They could tell that. Our Earth that we sat on, and the planets they could see with their naked eye, which was Mercury, Venus, Mars, Jupiter, and Saturn. The stars are so far away, they never saw them move, so they were just simply fixed lights on the celestial sphere. And they figured that those lights, because they moved throughout the year and reappeared, must have been because of they orbit around us or something. Who knows? So, the sun, the moon, the stars move very smoothly across the sky, but the planets, the non-twinkling objects that were little star-like things, for some reason, not Mercury, Venus, but Mars and Jupiter and Saturn would seem to progress in the same direction, but eventually they'd stop and go backwards a tiny bit before they'd come forward again. They call that retro back grade motion. Simply means to move backwards. Now, you see a picture of the football field and the track. What happens on a track? I guess that's not a track there on this one, but on a track, if you got the inside track and you're coming up on someone in a race, you still see them moving forward. As you pass them, it appears to you they're moving backwards because you've got the inside lane passing them. After you've passed them, you look over your shoulder, you see they're coming your way again, the same direction. So that point of passing them where they appear to move backwards, we call retrograde motion. So here's what the Greeks thought. They believed that, such as Mars, that red planet there, was orbiting the Earth because back then they thought the Earth was the center of the universe. Everything orbited around Earth, including the sun. So they thought that Mars orbited on its epicycle around its deferent. So the deferent would be its orbit around the Earth, and the epicycle would be its little twirling around its deferent there. So the epicycle we put in red, the deferent in yellow, and the apparent motion from Earth we put in blue, and that is the retrograde motion. So you see from Earth, it looks like it goes forward, then backwards, now forward again. Rewind this if you need to see it till it makes sense. So, yeah, there it is in big bold red. Greeks believed the planets moved in epicycles around their deferent. Ptolemy described this model of epicycles and deferents in detail, and it went well because everyone still believed we were the center of everything. That's called the geocentric. We say that's kind of egocentric because everything revolves around us, but yeah, geocentric, geo-Earth thought of belief. Then came the heliocentric model. Old guy named Aristarchus said, but wait, doesn't this make more sense if we orbit the sun? Sun is heliocentric centered solar system. So around 300 BC, Aristarchus proposed, yes, exactly that. Earth orbits the sun and it rotates on its axis. This is why we see the sun. Basically, what we know today is true. Three arguments against poor Aristarchus back in the day was the Earth doesn't feel like it's moving. You know, when you get in a car and accelerate, or like when back then when they're on their horse and riding, felt like you're moving. We don't see the interstellar parallax. That is, they didn't see the stars moving. As you drive by, ride a bicycle, whatever you're doing, you can see the buildings and stuff in the background appearing to move. But because the stars are so many light years away, they're too far away to move. You don't see them move. And lastly, you couldn't feel the wind in your hair, or lack thereof if you're really smart and good looking. So why the strong winds if the Earth's rotating? Well, there are. It's called a jet stream, but that's way up high, and we found that out much later. So in 16th century, Nicholas Copernicus, very famous man, came across Aristarchus' model of heliocentricity and said, this makes sense. Much to the church's dismay at the time, the Catholic Church did not like that at all, but it accounted for retrograde motion of the planets. and thus began the Copernican revolution. So there's 7 crucial statements to Copernicus' revolution. 1, the Earth is not the center of all celestial orbits. 2, the center of Earth is only the center of mass for itself rotating and for the moon orbiting us. 3, all the spheres, that is little planets, revolve around the sun, not us. We're simply one of those paths. 4, the ratio of the Earth to the sun is so much smaller and incomparable to the distance of the Earth to the stars. It takes light 8 minutes to get from the sun to Earth. It takes light over 4 years to get to our nearest star. It's very far away. Nope, there it is. So therefore, parallaxes cannot be observed. It's just too far away. 5th, we move, not the stars, relatively speaking. Everything's moving out there, but for our purposes, we're moving. We're the ones rotating. That's why I make the stars look up. They rise and they fall. They go up and down. The Earth moves, not the sun. Again, relatively speaking, the Earth is rotating. That's why the sun looks like it rises and falls. It's not orbiting us. Yeah, the sun is orbiting a black hole in the center of our galaxy somewhere, but that's a huge outer track. And finally, retrograde motion is not the planets moving backwards, but us simply passing them on the inner lap of the orbit. This picture amazed me when it came out in the 90s. Hubble aimed at a dark spot in our galaxy, opened up wide, and just kept collecting photons. When they finally developed the photo, we got this. Millions of galaxies, which contain billions of stars. Basically, which led to well, it didn't lead to this. This principle of mediocrity was thought way back when. Basically says, principle of mediocrity says, we are not the center of the universe. We're not superb, and the only thing that's cool, there are other planets similar to us, there are other stars, there's everything out there. We're not just it. So we're not the center of the atmosphere, center of the universe, center of everything. We're part of a huge, huge universe. We're mediocre, even though as a planet, we're way above mediocrity. But that's another story. So late 1500s, still long before a telescope, long before Galileo lived. Tycho, Teague, went by Tycho Brahe, made very accurate measurements using the same thing you built with a protractor, but his was big. He made a big sextant, and between him and his workers, they were able to very accurately measure the stars and take such accurate measurements that one of his younger colleagues who followed him, named Johann Kepler, was able to study his notes and come up with 3 laws of planetary movement which hold today. The first law is that our stars, our planets, do not move in a perfectly circle motion. We have elliptical orbits. The sun is at one of the foci. Of course, in the drawing down here, those 2 pins have a very wide focal points. They're far apart, so it's going to be very, very elliptical. But our sun, if you moved it to both points of the focal point, the points are super close together, but we're still not a perfect circle. So we do have an aphelion and a perihelion. This is highly exaggerated in the picture. At aphelion, we're a small fraction of a percent further away from the sun than we are at perihelion. But we're actually a little bit further away in the summer. It's just we're hotter because we're angled in that way. And the winter, the northern hemisphere is angled away from the sun, so we have a shorter day, hence less incoming solar radiation. Perihelion is the point of orbit nearest the sun. Remember, perigee is the moon closest to Geo, Earth. Perihelion, para-helio, sun, point of us closest to the sun. Likewise, aphelion, A away, helio, sun, furthest away. Law 2 of Kepler is basically that of equal area law. And I'll discuss this and more in part 2 of the history of astronomy.